All right, guys, this lesson is about arcs and chords. When we're done this lesson, we're going to be masters of relationships between arcs and chords and diameters. And to start off, we're going to jump into circle theorem number 2. This is our second circle theorem in this unit on circles. This is going to be the last lesson where I'm going to prove these theorems right here in the lesson, because these go pretty quickly. We've got a couple of theorems here that we'll prove. After this lesson, I'm going to do the proofs of the theorem separately because they get a little bit more involved. But this theorem here basically says in the same circle or in congruent circles, two minor arcs, such as these arcs AB and ED, are congruent if and only if their corresponding chords are congruent. So in this example, if this chord AB was congruent to this chord ED, then we could conclude that this arc AB must be congruent to this arc ED. This is true because in the same circle, we have the same radius. Or if we were in congruent circles, we could make that conclusion as well because congruent circles have the same radii. Why is this true? How do we know this is true? Well, anytime you want, you can draw a radius in a circle, like this radius AC and this radius BC. What do we know about all radii? All radii in the same circle are congruent, right? And we can do the same thing over here to this chord. And from this, you can see, these are radii as well, you can see that these two triangles are congruent by side, side, side. And if they're congruent, do we know that all of their corresponding parts are congruent? Corresponding parts of congruent triangles are congruent. And that tells us that the central angles of each of these triangles is going to be congruent. And if these central angles are the same, let's say this one measures x degrees, then this one measures x degrees, and that means that this arc out here measures x degrees because all arcs have the same measure as their central angle. Okay, could we use that idea here in this problem? In circle O, segment RS is congruent to segment TU. If the measure of arc RS equals 125 degrees, I'm going to go ahead and label that. Here's arc RS, it's 125 degrees. What is the measure of arc TU? Okay, well, since RS is congruent to TU in the same circle, we know that two arcs are going to be congruent if their chords are congruent. So the measure of arc TU is going to be 125 degrees as well. Try another one like that. If circle O is congruent to circle P and arc AB is congruent to arc CD, how long is chord CD? Okay, well, if these are congruent circles and then these are congruent arcs, then their chords must be congruent as well, right? Provided, of course, that the two circles are congruent. This is true either in the same circle or in congruent circles. And if these two chords are congruent, what could we conclude? Well, 6x plus 3, this expression that represents the length of chord AB must be equal to this expression that represents the length of chord CD. So this must equal 8x minus 9. Good, and we can solve that. For x, we'll subtract 6x from both sides, and we'll add 9 to both sides at the same time, and we're going to get 12 equals 2x. Good. These, of course, cancel. And if 12 equals 2x, then we get 6 equals x. Did we answer the question? Nope. Always read the question again. They want to know how long is chord CD. Shall we plug that back in? 8 times 6 is 48 minus 9 gives me what? Is that 38? Oh, this is not degrees. Excuse me. That's the length of a chord. So it's 38 units long. Good. Here's a good place to pause if you want to try one of these on your own. You can go ahead and pause the video. If circle C is congruent to circle D and arc ML is congruent to arc PQ, How long is chord ML? Okay, if these are congruent circles and these two arcs are congruent, then I know their corresponding chords must be congruent as well. And therefore I can conclude that these two expressions that represent the lengths of these chords must be equal. So 12x minus 13 must equal 9x plus 2. Could we solve that for x? Let's go ahead and subtract 9x from both sides and add 13 to both sides. Okay, I'm going to get 3x equals 15. And that means x equals 5. Did we answer the question? Nope. They want to know what? How long is chord ML? Okay, so I'm going to plug that 5 for x in here. 12 times 5 minus 13. This is 60 minus 13. And I believe you're going to find that gives you 47. So chord ML is 47 units long. All right, we've got two new theorems here that we're going to talk about. Circle theorem 3 tells us that if a radius or a diameter of a circle is perpendicular to a chord, then it bisects the chord in its arc. So what this is saying is that since this diameter GH, or you could say this radius DH, is perpendicular to this chord PQ, that it's going to bisect that chord, and it's going to bisect its corresponding arc. Okay, how do we know this is true? Well, you can draw a radius from D to P, and you can draw a radius from D to Q. The endpoints of every chord are equidistant from the center because because they're on the circle, right? And therefore, we could mark these two segments as being congruent because all radii in a circle are congruent. And so hopefully you recognize this as a perpendicular bisector. If we have this point D that is equidistant from the endpoints of chord PQ, then it must be on the perpendicular bisector of PQ. And if GH or DH is in fact perpendicular to this chord, then it must be a perpendicular bisector. Correspondingly, circle theorem 4 tells us that the perpendicular bisector of a chord, if we pick any chord in a circle and we establish its perpendicular bisector, that it's definitely going to be a radius or a diameter of the circle. And the reason we know this is the endpoints of a chord are located on the circle, and therefore they're equidistant from the center of the circle. And therefore the center must be on the perpendicular bisector of the chord. Again, we could draw those radii. We know they're going to be congruent. And so if the center of the circle is on the perpendicular bisector of the chord, then we can conclude that if we've got a perpendicular bisector of a chord, it must be a radius or a diameter. It's going to have to pass through the center of the circle. All right, based on that idea, let's try a couple of problems. Here in circle Z, they tell us the measure of arc RST is 160 degrees. Could we find the measure of arc ST and RH, which is a segment? So could we find ST? We want to find this. And could we find RH? Okay, so what do we know here? This whole angle here, this arc, is going to draw this so that we know we're talking about the entire arc here is 160 degrees. Well, it appears that this radius SZ is perpendicular to this chord RT, and therefore we can conclude that it must bisect that chord. And therefore, if HT is 6, RH is going to be 6 as well. It not only bisects the chord, it also bisects its corresponding arc, and therefore we could conclude that these two arcs are going to be congruent. And if these two arcs are congruent and they add up to 160 degrees, each of them will measure 80 degrees. Okay, here we've got circle W, and they give us that the measure of arc ABC is 165 degrees. So this guy here, okay, say this arc here, is 165 degrees. Could we find the measure of arc BC? I want to know this guy here. And could we find AC? All right, this time they want the whole length of the chord. Okay. Now again, we see this radius BW, and it's perpendicular to the chord, so we can conclude that it must be bisecting that chord. So if this segment is 9, this segment is 9, and therefore AC would be 18 units long. Now we also know that it's going to bisect the corresponding arcs, right? And therefore, if this entire arc is 165 and it's been bisected, it's been cut in half here, then arc BC must be half of that. It must be 82.5 degrees. All right, what's Dave up to this time? Dave is making a pattern for a woodworking project. In the drawing below, diameter AD is 20 inches long. Okay, AD, that's this right here. I'm going to go ahead and label that. This whole diameter is 20 inches. Good. And chord CE is 10 inches long. So this guy here, this chord, is 10 inches long. Good. How long is WX? All right, I got a green line on the paper, so I'm going to highlight in blue here. We want to know WX. Oh, this is interesting. All right, how are we going to find this? Any ideas? Pause the video and think about it for a bit before I drop this on you, okay? You're going to like this. That's a right angle. Well, first of all, this is a diameter and it intersects this chord at a right angle. So what did we just learn about that? These will be congruent. And if the whole chord is 10, then each of these segments will be 5 units long. Good. But also, what do we know about two lines that intersect at a right angle? It creates 4 right angles, does it not? So that's a right angle as well. And I'm going to ask you, how long or how far is it from W to point C? Do we know that? Well, WC is a radius of this circle, and the diameter of this circle is what? If the diameter is 20, then the radius must be half of that, must be 10 inches. Okay. Can we drop a little Pythagorean theorem on this now? Absolutely. We're after this here. Shall we call this y? And could we say that y squared plus 5 squared equals 10 squared? Right? And we're going to get y squared plus 25 equals 100. And we can solve this for y. We'll subtract 25 from both sides. We get y squared equals 75. And we'll take the square root of both sides. Swish and flick. And we get y equals the square root of 75. Could you factor that into the square root of 25 times 3? And could you simplify that to be the square root of 25 is 5 times the square root of 3. And our units would be inches. Good. I like how this problem pulls together all that cool stuff we learned about triangles and our Pythagorean theorem. All right, here's a great one to pause the video and try on your own if you want. It's similar to that last problem. Let's tackle this. In this drawing, diameter BD is 30 inches long. Okay, so we can go ahead and label that. This guy's 30 inches. And chord AC is 24 inches long. Okay, so this guy here is 24 inches. Good. How long is IJ? IJ. Okay, they want this piece in here. Okay. Well, I think we can do this. IJ is a radius of the circle, and it intersects this chord at a right angle. And therefore, we can conclude that this radius must bisect this chord. And therefore, if this chord is 24 inches long, then each of these segments must be 12 inches. Good. Okay. And if that's a right angle, I can conclude that that's a right angle as well. And if the diameter of this circle is 30 inches, how long is a radius such as this radius JC? It's going to be half the diameter. So this will be 15 inches. Okay. And we want to find this bit in here. Let's go ahead and call this x. Okay. Can we use some Pythagorean theorem here to find x? I've got a triangle hiding out there. I've got x squared plus 12 squared equals 15 squared. Good. And 12 squared is 144th. That's gross. 15 squared is 225. And I could subtract 144 from both sides. What do I have left over when I do that? Do I get 81? And now to solve for x, I can take the square root of both sides and I get x equals 9. Good. And you might have, if you were really astute, you might have recognized this as a Pythagorean triple right from the start. 9, 12, 15 is a multiple, in fact, of 3, 4, 5. So another good reason to know your Pythagorean triples makes that problem a little simpler. All right, circle theorem 5 tells us that in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center of the circle. So here in this example, if AB is congruent to ED, then we can conclude that FC must be congruent to CG. This segment that is perpendicular to the chord that passes through the center represents the distance from the center to that chord. Remember when we studied distance to a line, when we're talking from a distance from a point to a line, we're talking about the perpendicular distance. And therefore that means that each of these must be the same length. So two chords in the same circle or in congruent circles are congruent if and only if they're equidistant from the center. How do we know this is true? Well, if you are sensing a theme here, we can draw these radii and we can prove this. Both AC and CB are radii, and therefore they must be congruent. And CD and CE are also radii. They must be congruent as well. And now you might recognize that we've got, well, let's ask ourselves, what are we trying to prove here? Are we trying to prove that the chords are congruent or that CF and FG are going to be congruent? I would say if we know the chords are congruent, let's prove that CF and FG are congruent. And so that means that AB, we'll take AB and I'm going to give it 3 slashes, is congruent to ED. Okay. From that, can we conclude, can we prove that these guys are congruent? Okay. And what you might notice is that triangle ABC is congruent to triangle EDC. And the reason is we have side, side, side congruence. Okay. And now, could we conclude that since these two triangles are congruent, that all of their corresponding parts are congruent, including FC must be congruent to CG, because these are corresponding altitudes, right? FC must be congruent to CG. And I would say corresponding parts of congruent triangles are congruent. And yes, altitudes are corresponding parts in these congruent triangles. All right, let's use that idea in this problem here. In circle C, AB equals ED. Okay, so the length of this chord is the same as the length of this chord. Could we find CG, this segment right here? Well, if AB and ED are the same length, if they have equal length, then they're congruent chords. And two chords can be congruent if and only if they are equidistant from the center. And therefore, these two segments must be congruent. And if these two segments are congruent, can I conclude that those expressions that represent them must be equal? Absolutely. And can I solve that for x? Let's go ahead and subtract 5x from both sides. Well, we add 3 to both sides. I'm going to get 2x equals 6. And when we divide both sides by 2, we get x equals 3. Oh, but hold on, they wanted us to find what? They wanted us to find CG. So I'm going to go ahead and plug that in. 5 times 3 is 15, plus 3 is going to give me 18 units. All right, let's see if we got any more problems here. Oh, what's this? Wait, look at that. That could come in handy. All right, one last problem. In circle C, AB equals DE. So these chords are the same length. Could we find FC? Okay, if these chords are the same length, then these chords are congruent, and that can only happen if they are the same distance from the center of the circle. So these segments must be congruent to each other, and therefore we can conclude that these two expressions must be equal to one another. Okay, and we can solve that for x. Let's subtract 3x from both sides while we add 6 to both sides. I think we're going to get 33 equals 3x. If we divide both sides by 3, we get 11 equals x. Did we answer the question? Nope, they want to know FC. So let's go ahead and plug that back in. 3 times 11 plus 27. So that's going to be 33 plus 27 should give us 60. FC should be 60 units long. Okay. All right, I hope you guys found this video helpful. Good luck on the homework.